it's only really exciting. I think it's only really exciting when I try to tackle all three. So anyway, here we go. So there's a tradition called systems dynamics among modelers, where dynamical systems are modeled using things called stock flow diagrams. So here's a stock flow diagram for susceptible, infected, and recovered patients from some disease. So these boxes are called stocks. In this case, they're the different kinds of people. And you might assume a positive real number of people of each kind so that you can write down differential equations. So that's a continuum approximation. You could do other things too. These double arrows here, these big fat arrows, those are flows. And so the idea is that people will flow from one condition to the other. And the main thing that you need to know is to calculate the rates of these flows. You calculate the rates of these flows from certain variables. So these different bunches of words are things called variables. And variables can be computed from other variables. And so these blue lines called links indicate the way information gets used to compute variables, ultimately leading to the computation of the flows. There are lots of variants on this idea, and I'll actually be using a stripped down version later. But these diagrams are widely used in economics, population biology, epidemiology, and so on. And there's software already for dealing with them, and we've made some new software for dealing with them. So I'm going to work mathematically here with a stripped down version, just because it's easier to explain fast, where a stock flow diagram, for starters, it consists of 3 finite sets and functions between them. So there's a set of stocks, which are these boxes here. There's a set of flows, which are these big fat double arrows here. Every flow will have a source and target, but we're going to call them, following the tradition in this community, we'll call them the upstream and the downstream. So this flow F has S as its upstream and I as its downstream. And then there are these blue guys, these blue arrows called links. And the links will have a source, which is a stock, and a target, which is a flow. So in this stripped down version of stock flow diagrams, the flows are not computed from some intermediate variables, but directly from the stocks. And how are they computed from the stocks? Well, we need to equip this diagram here with some extra data, namely for each flow, a flow function that tells you how you compute that flow from the values of these stocks that have links pointing toward it. So you take the set of links whose target is that flow, and you pick a function from R to that set to R. So for example, this flow F here will be equipped with a function from R to the S comma I to R, because the number of susceptible people and the number of infected people both affect the flow of people from the susceptible to the infected stock. Now, each stock flow diagram gives you a set of ordinary differential equations having one variable for each stock, which say how the stocks change with time. So there's a systematic procedure to take one of these stock flow diagrams and read off a set of differential equations. For example, just do one example here. How does the rate of, how does the number of infected people change with time, di dt? Well, there are 3 terms there. A positive term, because people are flowing in from the susceptible condition at a rate equal to this function. They're flowing out to the resistant people at a rate equal to this function, and they're also flowing out to the dead people box at a rate equal to this other function. And so that illustrates the general procedure, and you can look at these other examples and you can see what the trick is. It's a very simple trick. And so it's a functor. So indeed, there's a category of stock flow diagrams, which I won't go into detail, but I've told you what the objects are. And there's a category of systems of differential equations, which we call dynamical systems, because some people in college didn't like differential equations, so we renamed them dynamical systems so they seem cooler. And a functor from stock flow diagrams to dynamical systems, which is this illustrated here on objects in this example. Now, modelers, I have to admit, like stock flow diagrams with extra bells and whistles. They like these variables. It helps you keep track of what's going on. They also like these clouds. When items flow out of the system considered and into the great beyond. We put them in a cloud if we're a traditional modeler. And our software handles these extra features and others, but I won't say much about them here because I don't have much time. Now, instead of StockFlow diagrams, you could ask, why not just work with the darn differential equations? And there are at least 3 important answers to that. It's a very important question. First of all, diagrams are easy to visualize, and they make it much easier to compose models. Compositionality is a big theme in category theory, and so that's one place category theory gets its foot in the door. Also, we can do other things with StockFlow diagrams than just convert them into differential equations. We can convert them into other things, and I'll talk a little bit about that. So what we should do is separate the syntax, that is the actual StockFlow diagrams, from the semantics, that is the way we have chosen to interpret them to gain flexibility. So just writing down the differential equations doesn't do that. And thirdly, and it's really hard to underestimate how important this is, most people actually find it easier to understand the diagrams than differential equations. Lo and behold, yes, it's true. Not everyone knows differential equations. If we were just leaving all this to trained mathematicians, maybe that wouldn't matter, but that's not how modeling actually works. In fact, there's a tradition called community-based modeling, which I'm a big fan of, in which diagrams let community members work with experts to help build models. Here's an example from India. So a team of experts on system dynamics were sent into this village to help them model the situation with their crops and livestock. And so here you can see the experts consulting with some of the villagers to build a model. And they could build a model by drawing StockFlow diagrams. And they don't need to have gone to college and studied differential equations to do that. The modelers do, but the villagers, of course, don't. Now, you'll notice something else here. All the people sitting around and talking here are men. And back in the background there's a woman. She just walked into the room somehow. And what is she doing? She's looking at the StockFlow diagram. And what she noticed, and this is a story that's been told in the literature, is she noticed that the StockFlow diagram was missing something. It was missing the fact that the imported cows, which they were starting to use, needed more water than the local cows. And so she pointed that out. She joined the conversation, and that helped improve the model. So that's a great example about how diagrams increase communication and allow for community-based modeling, where you actually have a group of people with different backgrounds engaged in making a model. That's what we want to do here. Now, there are epidemiologists who already use StockFlow diagrams to model the spread of disease, and this includes my collaborators, 2 of my many collaborators, Nathaniel Osgood and Xiaoyan Li at the University of Saskatchewan. I guess Xiaoyan is actually around at the conference, so you should ask her questions about things. She did most of the programming here. I'm a mere mathematician, but they are computer scientists specializing in public health. So they have expertise in both those subjects. And so they have told me a lot about what's going on. Most StockFlow modeling is currently done using some software called AnyLogic. It's quite powerful, but it has some big problems. It has no support for composing models. It has no support for something called stratifying models, which I'll discuss more later. But briefly, what that means is taking a model and making it more complicated by splitting a single stock or several stocks into more stocks. For example, you could have a simple model of disease, and then you say, hey, I want to break up each population into different age groups. They call that stratifying in the modeling community. It has no support for separating syntax from semantics. It just gives you the differential equation semantics. You can't turn a knob and say, hey, I want some other semantics. And it has no support for collaboratively building models, which is connected to it not being able to compose models. But basically, one person at a time interacts with the program. It's not free, and it's not open source. And in the grand scheme of helping the world, those 2 limitations are a big thing. You pay money to AnyLogic for this software. So our work aims to fix all those problems. Now, the ability to compose models is really crucial because realistic models are huge and complicated and built up out of many smaller parts. So Nate Osgood and Xiaoyan Li were actually brought on board by the government of Canada to help lead their COVID modeling. And after working on it for a while, this is the model they built. This is a page in any logic with zillions of stocks and flows. And there's no way you can see what's going on unless you zoom in, which I'm not currently able to do. But the point is that even if you zoom in, it's an ungainly system for dealing with things. You would like to have this broken up into parts. Instead, you just have to open up this page and deal with it. And really, basically, only a few people in the world could possibly internalize this page in their brain so that they know what they're doing. That goes completely against the collaborative approach. Okay, so we want to compose StockFlow models. So to do that, our software uses structured cospans. So the idea of them is very simple. Many of you have heard of it, but given any functor between two different categories, a structured cospan is a diagram in the second category, which is a cospan shaped like this, where the feet are actually L of certain objects in the first category. So you think of a structured cospan as a kind of morphism going from the object A to the object B, but it's a diagram in the category X. Now, if the category X has pushouts, you can compose these cospans in the usual way that you compose cospans by taking pushouts to get a big, get a cospan going all the way from A to C. So if you do this, you get, well, maybe a category with objects of A as the objects and structured cospans as morphisms. Actually, since composition of cospans is associative only up to isomorphism, you get something a little more fancy. You get a double category. We can water it down and turn it into a category, but fundamentally it's a double category. Now, an open StockFlow diagram is an idea that is an example of a structured cospan. So the idea is we have a StockFlow diagram here. I haven't written the flow functions, but I've written the rest here. But then we also have two finite sets, one S comma I and one comma R, that are mapped into the set of stocks in the StockFlow diagram. So, so we will use those as points at which we can compose StockFlow diagrams to get bigger ones. So this is a structured cospan using a functor from A to X, where A is the category of finite sets, where you think of a finite set of stocks as your finite set. X is the category of StockFlow diagrams, and L sends any finite set to the sort of trivial StockFlow diagram with that set of stocks and no links or flows. So that allows you to talk about a morphism from this thing to this thing. You convert this in a free way to basically to a StockFlow diagram. So open StockFlow diagrams are going to be morphisms in a structured cospan category, or really double category, which I'll call open StockFlow. I'll think of it as a category for now. So you can compose them. Yay, it's a category, you can compose things. But besides composing structured cospans end to end, our software can also compose them in more complicated ways that are more useful than just being limited to end-to-end composition. We could have 3 different open StockFlow diagrams with some of the stocks repeated in various ones, and we may want to stick them together to form a single StockFlow diagram given by this kind of pattern. Well, we can do that because under some mild conditions listed here, structured cospan categories are always hypergraph categories. A hypergraph category is a fancy kind of category where you can compose the morphisms or operations in patterns that look roughly like this. So categories are just sort of the bottom rung of a totem pole of different more complex structures in which you can compose the morphisms in more and more complicated and interesting ways. And hypergraph categories are among those. I should add, by the way, that although these pictures are all planar, you can switch wires across each other in a hypergraph category. Hypergraph categories seem very confusing at first, but it turns out you should think of them as algebras of a certain operad. And Brendan Fong and David Spivak have a nice paper on hypergraph categories where they explain that point of view. And then Kenny Corser and I wrote a paper where we prove that structured cospans give you hypergraph categories. Okay, so we can compose to our heart's content. But our software can also stratify StockFlow models, that is, refine them by breaking stocks into more stocks. And for this, we use pullbacks in the category StockFlow. For example, products. So here's a simple susceptible, infected, resistant StockFlow diagram. Here's an even simpler thing where young people turn into old people. Normally you would have more age groups, but here I'm just drawing 2. And then if you take the product of these, you get a StockFlow diagram, which has the susceptible, infected, and resistant people stratified, in the language of modelers, into young and old. So you can have more flexibility for modeling and keep track of things in a more fine-grained way. Okay, so we created our software that does this stuff with Evan Patterson and Sophie Libkin, who are real experts on categories for computing. And our first paper on this was written with a whole team here called Compositional Modeling with Stock and Flow Diagrams. That software, called StockFlow, used AlgebraicJulia, which is a framework for high-performance scientific computing using categories. And if you've been dealing with categories in computation recently, you've probably heard about it already. It was developed by a large group of people, including James Fairbanks, Evan, Sophie, and many others. And I should add that the idea of composing structured cospans using undirected wiring diagrams via hypergraph categories was nothing new to our work. It had already been implemented in AlgebraicJulia in this paper here and in software. And that shows you one example of the advantage of working in the AlgebraicJulia ecosystem, is that people can develop general methodologies framed at a high level of abstraction, explicitly discussing categories and so on. And then other people can reuse those ideas in other pieces of software. So using AlgebraicJulia, we created this software package called StockFlow. You can get it on GitHub, and it lets you build StockFlow diagrams, look at them, make them open, compose them, apply various functors to interpret them, numerically solve the differential equations, if that's how you're interpreting them, and also stratifying them using pullbacks. Now, what are the other functors that you can use to interpret them besides the differential equations? Well, so besides this one that maps a StockFlow diagram to a dynamical system, one example is you can map it to something called a system structure diagram, which is another type of diagram used in the system dynamics tradition. It's very simple to explain. A system structure diagram is just a diagram of this shape in the category of finite sets. So it has your stocks, your flows, your links, and as before, but what it just lacks is the flow functions. So the category system structure is just the category of functors from this diagram here, D, to the category of finite sets. So a StockFlow diagram, which is what I've been mainly talking about, is a system structure diagram equipped with the flow functions. So that means that there's a forgetful functor that takes a StockFlow diagram and forgets the flow function. So here's a StockFlow diagram, and bingo, I'll hit it with a forgetful functor, and now it's a system structure diagram. So of course, that's a very simple idea, but it's part of an idea, bunch of ideas in system dynamics. They mainly use 3 styles of diagrams. I won't talk about the third, called causal loop diagrams, but there are essentially forgetful functors going down the ladder here. And what's the point? Well, they don't talk about forgetful functors. What they talk about is that they're going to try to build a StockFlow diagram, but they're going to start with something simple called a causal loop diagram, and then keep adding information to it to first turn it into a system structure diagram and then a StockFlow diagram. And you can read tutorials for people who know nothing about math about how to do this, about how you go up the level, and like what questions should you ask your local people to elicit the extra information that lets you climb up the hierarchy. So I'm really fond of this idea. I'm fond of the idea of building systems one stage at a time through a kind of poset of forgetful functors. The forgetful functors do a couple of things. One is they let you check that you're on the right track. You've built your system structure diagram. If it's all in software, you can just hit a button and bingo, you can see the causal loop diagram and make sure you did things the way you intended. Or another thing that is perhaps more important is that if you have, for example, I'll pick a StockFlow diagram, and then I want to throw out the flow functions and change them to build a new model, I can just hit it with this functor, go down to the level of a system structure diagram, and then by hand insert the new changed flow functions. So you can climb up and down this hierarchy in the modeling process. And this is just an example, of course, of a very general paradigm, which is what I'm enamored with. So another thing is that functorial semantics lets you build big models out of smaller pieces that are described using several different choices of syntax, as long as they all map to some common semantics or even some common syntax. So for example, besides being able to turn StockFlow diagrams into dynamical systems, you can turn Petri nets, or Petri nets with rates technically, into dynamical systems. And that latter has been implemented in AlgebraicJulia before we came along in this paper here. So what that means now is that once we get everything up and running, I could build an open StockFlow diagram. You could build an open Petri net. We'd like to stick them together. We can't do it directly because they're different kinds of things. But one thing we can do is we can turn them both into open dynamical systems and then compose them. So this provides a very disciplined way of building complicated models out of pieces of disparate sorts. Of course, people are always building complicated models in real life out of pieces of disparate sorts, but usually it's in an mathematically imprecise way that causes all sorts of problems when you try to glue them together. But here you have the potential for really having everything under control. Then with Eric Redekop, a student of Nathaniel Osgood, we made a graphical user interface for StockFlow called ModelCollab, which is also available on GitHub. And this paper of ours here explains that in detail and also explains the AlgebraicJulia in great detail. Sorry, I seem to be getting stuck in some time loops here. Okay, so ModelCollab runs in your browser. So the idea is that teams can collaborate to build StockFlow diagrams, either by several people interacting with the same window at the same time, or more usefully, I could build a model, I could save it, you could build a model, you could save it, and then I could import both of those models and then glue them together. I can actually just drag boxes around and glue them together. And that is actually doing this operatic composition of StockFlow diagrams, open StockFlow diagrams. And the great thing about ModelCollab is that you don't need to know anything about category theory or AlgebraicJulia to use it. You just need to know how to interact with these pictures by dragging things around and sticking them together. So all the fancy math has been black boxed. And indeed, this leads to a hypothesis of mine, or it doesn't lead to it, but it's part of a hypothesis of mine. It's evidence for it, perhaps, that to become widely successful, applied category theory should make itself invisible. Us mathematicians like category theory, but believe it or not, most people don't even know what it is. So we have to hide it. So I just hope that I illustrated three basic principles here of modeling: compositionality, functorial semantics, and stratification, which is what us category theorists would call pullbacks. When you fit all these together, they fit together nicely in the double category framework, which we haven't really fully gotten into the software. StockFlow does implement all three of these. ModelCollab only implements about 1.5. It just has one choice of semantics implemented so far, but we're far from done. And so what I hope I've shown is that there's a lot of room for new things to do here. And it's not really about StockFlow diagrams so much as a new approach to modeling using categories and software. Thanks.
Okay, thank you. So let's take questions. I don't know if I should throw this or go around. Yeah.
Thanks so much. I love your work, as we all do. I wanted to just comment on a direction related to your last comment, about invisibility and multiple perspectives. There was once a major conflict in Cambridge, Massachusetts, in which for a year all development ceased because Cambridge, known as the Free Republic of Cambridge, halted development until stakeholders who were residents could get to an agreement with stakeholders who were investors. And they were finally unable to talk to each other. I was wondering if you would be interested, in pushing this development towards the direction of enabling this conversation. I happened to, at that time, have taught an IAP course in which the residents designed their own causal loop diagrams,
Oh,
and the
cool.
developers causal loop diagrams, and they were quite different. And
I
then
bet.
they came together, and there was the discussion that enabled both of them to see it. And that's sort of a, so to speak, a little orthogonal, but very related to what you're doing. And the city was very pleased because after that discussion, an academically based discussion, the two started to talk together. So,
Yeah, that's very interesting to me. So MIT has been the locus of origin of this system dynamics tradition. So it's in some ways not surprising that that's where it happened, in Cambridge, Massachusetts. But anyway, I'd be happy to talk to you afterwards about this, and hopefully, yes, in the longer run, when the software is polished, we meaning everybody could use it for situations like this. But system dynamics is already a good way of bridging those communication gaps.
All right, thank you. Thank you for the talk. I want to ask a point of clarification. If links express dependencies between stocks and flows, if I find more information about my model that determines a link, like, is that what stratification does? It allows me to turn that link into another system?
That's not what people call stratification. So I think it's a perfectly good thing to do, and it is an important way to improve or change a model. But stratification, as far in my limited understanding of the modeling tradition, means just breaking stocks into multiple stocks according to some new characteristic of the stock, like age groups and sex is a very common thing. So you first build a somewhat simple model of infectious disease like this, and then you say, oh, but wait a minute, we're discovering that old people are much more susceptible to the disease. So you would like to go bingo, like multiply this by a bunch of age groups. But what you're talking about is a different method of refining diagrams that is also important. And yeah, I think category theory can help clarify, ultimately, help clarify all these different ways of modifying diagrams.
Thank you.
So thanks everyone. I think it's time for us to move on to the break. But everyone, thank our speaker again.
Thanks. Please talk to me on Zulip if you want. Thanks.